This video is for Chapter 32 on field effect transistors, particularly sections 32.1 and 32.2. The field effect transistors we'll be looking at here are what are known as MOSFET transistors. That stands for metal, oxide, semiconductor, field effect transistor. Quite a mouthful, which is why we usually just call them MOSFET. And quite often we even leave out the MOS part and just call it a field effect transistor, because junction field effect transistors, which are the other type of field effect transistors, aren't used much except for in the electret microphones, which we've looked at a little bit earlier. The symbol is intended to remind you of the metal oxide semiconductor nature, because we have the gate, which is the metal. Then we have an insulating layer, which is silicon dioxide, the oxide layer. Sometimes it has some silicon nitride in it also, but in any case, it's an insulator. And then we have the semiconductor. And because these are enhancement mode devices, we usually do a dashed line for the symbol. And the two other terminals here are the source, which is the source for the charge carriers. So for an MFET, which is using electrons as charge carriers, so negatively charged, the N stands for negative. So negative carriers. The source is the negative end of the device. The other end, where the carriers are taken back out of the device, is called the drain. So the electrons in an MFET move from the source to the drain. We get current flow in the conventional current flow will be in the opposite direction from the drain to the source. There's one more terminal for a field effect transistor, which is the body. But in the power field effect transistors we're using, the body is always connected to the source. And what that does is it provides a diode between the source and the drain. And this body diode is always connected in such a way that under normal operation of the transistor, it's reverse biased. Because when it's forward biased, it just conducts, and then you don't have any control from the gate of whether the transistor is on or not. So our usual use for these field effect transistors is with this body diode reverse biased. And the arrow here is going from the source to the channel here, and it's from the source to the drain in the body diode, so that the arrow and the body diode go in the same direction. And an easier way to remember which way that arrow goes is that for MFETs, N is in. The arrow points in on an MFET. Let's now take a look at the characteristics of this transistor. And what that means is we will be looking at the current versus voltage plot. So, what current are we talking about, and what voltage are we talking about? Well, the current, the only current we're interested in is the drain to source current, because there is no current through the gate. The gate is a capacitor, and there's no DC current. The voltage we're talking about, we have the gate to source voltage, and we have the drain to source voltage. So there's two different voltages we could be talking about. And what's usually done is to draw this thing with the drain to source voltage as the x-axis, and to draw different curves for different gate voltages. So there's two different gate voltages that are particularly interesting. One is where the gate to source voltage is 0 volts, or more precisely, less than some threshold voltage, and I'll say threshold for the N transistor. And what happens there is we have IDS is 0. Transistor is off. Okay, the other thing we do is we have characteristic looks something like this, where VGS is a lot bigger than the threshold. The transistor is on, and we usually use it in this linear region here at the beginning. So IDS is VDS over some on resistance. And then there's a saturation region out here. This is the saturation region out here, and this is the linear region down here. And we usually want to use this in the linear region because what we're trying to do is to keep the power dissipation in the field effect transistor as small as we can. When the transistor is off, there's no problem. We can be way out here. The power is the voltage times the current. So if the current is 0, the power is 0. We don't dissipate anything when the transistor is off. And this 0 amp for the current is really pretty good. The field effect transistors have pretty low leakage. It's specified on the data sheet, so you can look it up. But it's quite small, and generally the power you lose when the thing's off is tiny. What about when the transistor's on? Well, there we've got a large current, because remember we're trying to control the current with this field effect transistor, and the power is going to be VDS squared over R on, or you can also write that as IDS squared times R on. Since it's current we're trying to control, it's usually easier to look at it this way. If we make the on resistance small enough, we can have this power dissipation be quite small. But it is sensitive to the square of the current. So if you're trying to do something where you say, okay, I want to double the current, if you want to keep the power as low, you may have to take the on resistance down by a factor of 4, which means usually switching to a different transistor. There is something here that's misleading in this whole picture, and that is I've only drawn 2 curves. And in practice, there's an infinite number of curves for different voltages of the gate. And what happens at those lower voltages is that you get a curve that's intermediate. The on resistance here is larger. You get a lower slope on a current versus voltage. Resistance is 1 over that slope. So here you have a larger on resistance. This is for VGS bigger than the threshold, but not as big as I had in that first curve. And the reason this is important is because on the data sheet they'll give you an R on specified, and it's going to be a tiny number. They're going to say, oh wow, this thing's only got 10 milliohms or something like that for its on resistance. But that's at a particular gate voltage that they were measuring at. And they usually pick the largest gate voltage that their transistor can handle because that'll give them the lowest on resistance. You're probably not going to be operating at those voltages. You're likely to be operating at a much lower voltage, in which case you get a curve more like this one with a much larger on resistance. So you need to actually either find on the datasheet information about what the on resistance is at the voltage you'll be using, or if you don't find it on the datasheet, you'll have to measure it. So that you don't assume, oh, I'm not going to have much power dissipated here when your resistance is much larger than you might have guessed from the datasheet. Okay, that was the MFET. What about the PFET, which is the other type, using p-doped semiconductor rather than n-doped semiconductor? Well, the symbol is much the same because it's still metal oxide semiconductor. It's still enhancement mode. The difference is that because it's p-doped, we draw the arrow for the body going the other way. And I like drawing the source on top and the drain on the bottom. I mean, obviously you can draw it either way up, but the body is connected to the source. And the source here is the positive end now because it's the source for the holes in the p-type, and the drain is the negative end. So this is the PFET with positive carriers, and the gate is still the gate. When does this one turn on? Well, we're still interested in the gate to source voltage, but the source is now the most positive thing in the system rather than the most negative thing. And so what we have is that if VGS is greater than V threshold for the P transistor, which is less than 0 volts, as a negative number. So if it's greater than this, then we're off. And if VGS is much less than V threshold for the P transistor, then we're on. Okay, so everything is kind of like the MOSFET, except for that we've swapped the roles of positive and negative. So the source is our most positive thing in the system. The gate has to be lower in voltage than the source in order to turn on, and the drain is again current flowing in the opposite direction. So current now flows from the source to the drain, whereas in the MOSFET, electrons flowed from the source to the drain, giving us a current in the opposite direction. I probably should put the body diode on this picture also. And the body diode is again reverse biased, which it has to be for the transistor to function as a transistor. Okay, if we draw this thing, we would end up with negative currents from drain to source and negative voltages from gate to source. So what I'm going to do is draw this thing as minus VDS on this axis and minus IDS on this axis, just so I can draw everything in the first quadrant rather than having to draw down in the fourth quadrant. I always get stuff upside down there. And things look very much like they did before. We still have an on transistor, and we still have an off transistor, and this is for VGS bigger than V threshold P for off, and this one is VGS much less than V threshold P, which is in turn less than 0 volts. So this is a very negative voltage, which means the gate, being well below the source, turns this thing on. Okay, so we've looked at the two. This characteristic here looks very much like it does for the MOSFETs. The one difference you'll find is that for comparable size PFETs and MOSFETs, the PFET will have a higher on resistance, and that's just sort of intrinsic to the fact that holes are less mobile than electrons. Okay, so what do we do with these transistors? We looked at something in a previous video that had a single MOSFET switching, and it was just switching on or off for resistive load. But there's something else that we more commonly do, and that is to have something where we want to have the output being either pulled high or pulled low. And to do that, we need two transistors. The transistor on the top, connected to the positive power supply, is a PFET. And the transistor on the bottom, connected to the negative power supply, or ground in our case since we're using a single power supply, is an MOSFET. So we have PFET up here, MOSFET down here. This arrangement, where you have both positive PFETs and negative MOSFETs, is often referred to as cMOS. And the C stands for complementary. And MOS is metal oxide semiconductor, just as before. So a cMOS circuit has both a PFET pulling up to power and an MOSFET pulling down to ground. What are the possible states of CMOS? Well, If both transistors are turned off, the output is disconnected. This is sometimes known as the high Z state. High impedance, there's basically no connection to either power or ground, and that's both off. If we have just the MOSFET on, we have a 0 volt output. So connected down to ground here, but not connected up to power supply. We can have, well, let's give this a voltage here. Let's call this 5 volts. We can have 5 volts on the output if the PFET is on, but the MOSFET is off. And we can have this 0 volts and 5 volts actually be very, very close to 0 volts and 5 volts because we can make those resistance, the on resistance of these transistors, quite small. There's one other state, and that is what happens when we turn both the MOSFET on and the PFET on. Well, we have a low resistance from 5 volts to the output. We have a low resistance from the output to ground, and that means high current. Basically a short circuit. We don't want that. We do not want to just be pumping current from power supply to ground without doing anything useful. So that's known as shoot-through current. And we usually want to set up our circuits to avoid getting shoot-through current. That's not always easy to do. Let's take a look at what we can have happen. So let's look at sort of a VGS now on the x-axis, gate to source voltage. We can have, let's say we're going from 0 volts to 5 volts as our power supply. When do we have the MOSFET on? So let's look at the MOSFET. Do that one, I guess, in pink here. If we're below the threshold for the M transistor, it's off. But above that, it quickly turns on. What about the PFET? Well, the PFET, so now, if we put the, I should change this label here from VGS to just V gate, because what I'm going to do here actually is to connect those two gates together. And this is now PFET on top and MOSFET on the bottom still. But if those two gates are connected together, the gate voltage is the same here. At 5 volts, the gate to source voltage then is 0. All right, so if we look at VGS, VGS here is 0 volts to minus 5 volts. If the gate voltage is 5 volts with 5 volts on the source for the PFET. All right, so this is going to be off until we get down to V threshold for the P, or 5 volts plus that. And then it's going to turn on, and at lower voltages, the PFET will be on. So at very low voltages, down near 0 volts, we're going to have the MOSFET off and the PFET on, and that's high output. At very high voltages on the gate, near the top voltage on our system, we're going to have the PFET on and the MOSFET off. So that's going to give us a, okay, so we've got, sorry, the MOSFET on and the PFET off. That's going to give us a low output. And then there's this region in the middle here where we have both transistors turned on. That's really bad. That's where we get shoot-through current. Now, one thing we can do is we can reduce our power supply voltage because these thresholds don't really depend on the power supply voltage. So if we reduce the power supply voltage, these get closer and closer together, and you can make them so that, in fact, you have a region where both transistors are off rather than both transistors being on. And that's what's done for really low power cMOS if you're doing something like a watch, where you want to run for months on a battery. You move those things so that both transistors are off when you make the transition. You turn one off completely before the other one turns on. That's great for doing very low power things, but if you're trying to do something like a power amplifier where you want to be able to put high voltages and high currents, because I mean if you're driving a loudspeaker for instance and you have an 8 ohm load, you can't just say, well, I'll put a tiny little voltage there because then you won't get any power to the loudspeaker. You have to go with a large enough voltage for the circuit you're driving, for a loudspeaker, for a motor, anything where you're trying to deliver a high voltage to something. You don't have the choice of saying, well, I'll just make the voltages smaller. And so what people can do is sometimes they will pick transistors with big thresholds. Another thing you can do is say, well, there's this bad region in here. What makes that region bad? I get a high current. That's not a problem in terms of heating up the transistors or wasting power if I can do it for a short enough period of time. So what is often done if you have to do power transistors is say, okay, I've got this region in the middle where I have the shoot-through current, and what I will try to do is move the gate very rapidly from one state to the other state or back, and spend very, very little time in this region. So you'll get a spike of current, but it'll be a very short duration and so won't contain a lot of energy. There'll be a power spike, but the total energy in that spike will be kept small, and so you can still keep things fairly efficient. I mean, you do lose some energy during that shoot-through current time, and there's not a lot you can do about that if you have to run a high voltage and you've got your transistors with fixed thresholds. So basically the solution usually is run fast, make that gate change very rapidly. And we'll look at that in a subsequent video, how to make a rapid transition on the gate.